This is lecture 2-4, all about the library of functions and piecewise functions. Some of this is going to be review for you guys, which means that you might not need to watch all of the beginning if you guys can do the parent functions already. All right, this matches notes on page 7 and 8 of the student note packet. So if you go to the pink chapter 2 pages 7 and 8, this will match those pages there. All right, so the first parent function we're going to talk about is the constant function. That is y is equal to b, or f of x is equal to b, where b is some real number. So in this example, I've got the value of y as 3, right? And then when we're looking at the constant function there, we don't have x. X isn't part of our equation. All right, next parent function is a line. The parent function is y is equal to x, or f of x is equal to x. So for every value of x, y matches. Next, we've got the square function. So all of these functions come from Algebra 2, which is why I'm going through them pretty quickly. We've got the parabola. The parent function is x squared. So for every value of x, right, we square and get the value of y. So those are the parent function points. The cubic function, y is equal to x cubed, is our next parent function. So again, remember, when we cube a negative number, it's still negative. And those are some of the parent function points. Then we've got the square root function. So remember, we have a domain restriction on the square root function. The domain is all the values of x that are greater than or equal to 0 if we're looking at the parent function. So I'm only going to pick values of x that fit in that domain, and I'm going to pick nice ones here that are perfect squares. So when I take the square root, we're only taking the positive square root there because of that domain restriction. And those are some of the parent function points that we graph. Cube root, it's the cube root of x. So with cube roots, we don't have domain restrictions because you can take the cube root of a negative number. So I'm going to pick nice numbers here to take the cube root of. This is -2, -1, 0, +1. Some of the the values that we plot on the graph of this parent function. All right, the reciprocal function, a lot of times I'll call it the inverse variation function, but the parent function is 1 over x. It looks like that. So we found in one of the last lectures that this is the inverse of itself. If we were going to pick some numbers, doesn't really matter. 0 doesn't work, so we do have a domain restriction there. So 0, we're undefined. We've got an asymptote. We get -1. Doesn't get defined at 0, we get +1 and then 1/2. Right? So as long as you can make a t-table for all of these parent functions, what we do on the next page is going to be pretty straightforward. Absolute value function is our last parent function here for the library of functions. Right, when we take the absolute value, we get back the positive value there. All right, so what we're really getting at in this lecture is piecewise functions. So piecewise functions are going to take all of those functions that we just graphed on page 7, and it's going to put them together. It's going to take a piece of one with a specific domain and graph it next to a piece of another with another specific domain. So as long as you guys can make t-tables that represent the points to plot for each of the parent functions on page 7, you guys should be good at graphing piecewise functions. All right, we can also call them change of rule. I probably won't refer to them that way, but you might see that in the textbook. So just know piecewise functions, change of rule functions, they're the same thing. So we've got our first piecewise function, and it's defined in chunks. So x squared 2 and x plus 2. And each of those pieces are defined on its own domain. So we have to pay really close attention to that when we do the next part. So the first question asks us to find the values of f of -2, f of 0, and f of 3. So the domain matters here. When I'm plugging in -2 for x, we have to figure out which function we're actually going to use. Are we going to use x squared? Are we going to use 2? Or are we going to use x plus 2? So we go to the domain restrictions. Where is x -2 in these domains? Well, -2 fits into this domain. It is less than 0. So we're going to use x squared to evaluate f of -2. I'm going to replace x with -2, and then we are going to simplify. So f of -2 is +4 in this case. All right, then we move on. F of 0 is the next piece. Now, again, when x is 0, where does that fit in our domain? Well, it fits here with 2. So f of 0 is 2. There's nowhere to replace x because there's no x in this constant function. Last case, f of 3. Now 3 fits in this domain. 3 is greater than 0. So we're going to replace x with 3 and x plus 2. So f of 3 is 5. Next up, we're going to graph this, and I'm going to do this by color coding so you guys can see it a little bit easier. We have to graph this in parts. So the first part I'm going to graph is x squared, but we're only graphing the parent function x squared for all the values of x that are less than 0. So imagine the parabola x squared, but only including the values of x that are less than 0. It's just the left half of the parabola there. So I'm going to sketch in some of those points. 0, 0 is a point. -1, 1. -2, 4. I'm scaling by 1 here. -3, 9. Right? And we've got our parabola on the left side. Now there's one issue here. Our domain says all the values of x that are strictly less than 0. So strictly less than 0 means that at the origin, we actually can't have a closed circle. We need an open circle at the origin that represents the values that are strictly less than 0. I'm going to connect the dots to draw the curve, and because it's all the values of x less than 0, we're going to have an arrow pointing to the left. All right, the next piece then, that middle piece, says this. When x is equal to 0, our function is 2. So when x is equal to 0, our function is 2. That means we're just plotting the point 0, 2. Now this is a closed circle because x is equal to 0 at that point. It is defined there. And then the very last piece of our piecewise function comes from x plus 2. That line, slope of 1, y-intercept of 2. That's for all the values of x that are greater than 0. So we're taking a look at all the pieces of that line that are to the right of the y-axis. So a line with a slope of 1 and a y-intercept of 2 is going to look like this. And I'm going to connect the dots. All right, now one more thing I'm going to note here. Because the domain was strictly greater than 0, again, at that y-intercept, I'm going to have an open circle for that piece of my function. Now, technically, it's a closed circle because 0, 2 is the same point, and we're defined in that middle definition of our piecewise function. So if you're doing this in pencil, it's okay if you only have a closed circle there. But just to make it a little bit clear in color, I'm going to put an open circle in purple that represents the values of x that are strictly greater than 0 for x plus 2. Okay, if you've got a pencil, just graph it as a single dot. That's fine. The last piece asks us this, is f continuous on its domain? So here's the question. If you were starting left to right, moving left to right, if you were to put your pencil on the paper and trace this function, would you ever have to pick your pencil up to get from one piece of the function to the next? And we see this here. There's a little bit of a jump. We would have to pick our pencil up and we'd have to move it from that blue function up to that green dot or the purple function. So this is not continuous because we have the jump there. All right. I'd like you guys to pause the video and give this a try. Graph this piecewise function and then come back and check your answer against mine. All right, so there's two pieces to this piecewise function. The first is the absolute value of x, and we're only defined along -2 to 0, the interval -2 to 0. So we actually cannot have an arrow coming off pointing left. So if you had an arrow on that side of the piecewise function, get rid of that, because our domain is restricted to -2 to 0. So we do include -2 in that value. There's a closed circle at -2, 2. But at the origin, at 0, 0, we have an open circle because x is strictly less than 0. Then moving on to the cubic function, again, we have a domain restriction. X is strictly greater than 0. So at the origin, we still have an open circle. There should be no closed circle at the origin. We don't have any definition for when x is equal to 0. And then I'm just going to graph the points that represent that cubic function. So 0, 0, 1, 1, and then 2, 8. And those are for all the values of x greater than 0. So we do have an arrow coming off and pointing to the right. Then we have a question, is this continuous on its domain? The problem is that hole at the origin. So we have a hole there. We don't have any definition for when x is equal to 0. So we actually don't have continuity. So this is a no. We haven't jumped like we did in the last example, but we don't have a definition for when x is 0. How about going backwards now? So we are given the graph this time, and we want to write the equation of the piecewise function. Now, there might be different ways that you could go about writing this. There could be many options here. So let's think about this. I'm going to talk about this option first, okay? So I'm going to move left to right. Let's talk about what I just graphed in blue. That looks like a line, so we need to find the equation of the line, and then we'll include the domain restrictions there, or you can include the domain restrictions first. So this is all the values that are greater than or equal to -5 and less than or equal to 0. So we're including the equal signs on both sides because we have closed circles there. And that is actually really tricky. That's not -5. That's actually -4. Okay, so there's our domain. We just need to figure out what the equation of this line is. So we have a y-intercept of 1, 2, 3. So I know it's going to be +3. And let's figure out what the slope is here. So rise over run. 1, 2, 3, 4. We go to the right 4 and up 3. All right, so rise over run, 3 over 4x plus 3 is our equation for that line on the domain -4 to 0, inclusive of both of those. Okay, so that's our first piece. I've kind of squished this in a little bit here. Let me do the curly brackets. Second piece, let's do this in a different color. Now, we've got an open circle at 0, so that's important. Okay, and we go closed circle at 5. So 0 is strictly less than x, which is less than or equal to 5 here. That's our domain. Now, different ways you guys can go about representing this. How about we represent that as the absolute value of x? That works. Another way you guys could have done that is just x. Y is equal to x. Okay, different options there. Last example, go ahead, pause the video, try writing an answer on your own, and then coming back and checking. All right, we've got -x to represent the left portion. On the domain x is less than or equal to 0. We've got a closed circle there at the origin. And then the right portion is 3x, where x is between 0 and 2, inclusive of both of those values. I do want to point out that this is an example of something that is continuous. We don't have to pick up our pencil moving from left to right to trace the graph, and we also have definition at every point, so there's no open circles there. Another way that you guys could have chosen to represent the right portion, if you put the absolute value of x, that's also fine, right? That could work as well. All right, that is it for 2-4. You guys can get started on your homework now.